Just like in arithmetic sequences, we had a formula to find the sum. We have the same thing in geometric. And these are not formulas that I'm going to ask you to memorize. I just want you to be able to use them. So if you're going to find the sum of a geometric sequence, this is your formula. Now, this is for a finite one. It has to end somewhere. And just like before, it's the nth sum. We have a1, so our first term, times 1 minus r to the n, divided by 1 minus r. The place where I most commonly mess this up is this r to the n. That is on the inside of the parentheses, so just keep that there. Strange things happen because I tend to want to put it on the outside. And this only works if the common ratio is not 1, because clearly that would be dividing by 0. You can't do that. All right, so let's apply this formula. So we're going to find this sum. It's written in sigma notation. You can definitely use Desmos or the calculator to just, have it generate it. But I want to show you how to use this formula as well. So the reason we can use this, do you see that this is the formula a1 r to the n minus 1? Okay, this thing is our formula for a geometric sequence. So we know that this is a geometric sequence because it's in that format. So since it's in that format, we can use the sum formula. So we are looking for the 12th partial sum because we start at 1 and we go to 12. And a1, to find our first term, you can either plug in 1, like actually plug it in, and you get 4 times 0.3 to the 1 minus 1, which is going to be 0.3 to the 0, which is 1. So your first term is 4. Or you could have looked at this and said, look, I know that's going to be a1. And then 1 minus r, your r is your common ratio. It is always going to be the base of that exponent. So 0.3 to the 12th. I should probably write bigger, so that way it's not so sloppy. Divided by 1 minus 0.3. Okay, you're putting this into the calculator just to make sure you've got all the parentheses in there where they belong, and we get 5.714. All right, let's try the next one. This time it'll be a 10th partial sum because we're going from 1 to 10. Our first term is 2, or you can get that by plugging in 1. And then 1 minus our common ratio is always going to be the base of that. So 0.25 to the 10th over 1 minus 0.25. And we're just going to put that all into the calculator. See what magic it comes up with. 2.667. Now, something kind of interesting. With arithmetic sequences, we could only do finite sums, okay? If it keeps going on and on, there's no reason to find the sum because they just kept getting bigger and bigger. We can find the sum of some arithmetic or of geometric series, okay? The reason this works, do you remember what we said, what the graph looks like of geometric sequences? Remember their exponential growth or decay? So if your terms are exponential growth, okay, it keeps going on and on. If you add all of these up, it's just going to get bigger and bigger and bigger, okay? So it does not make any sense to find the infinite sum of exponential growth because it's just huge. It's just infinity. But if you have exponential decay, when you start adding these terms up, these terms down here are really, really close to 0. Eventually, they get so close to 0, they don't really matter in the sum. So if you have exponential decay, the sum of these things actually approaches a number, okay? So if your common ratio is between -1 and 1, if it is exponential decay, you can find an infinite sum. And it's a really simple formula. It's a1 divided by 1 minus r, okay? But it only works if your common ratio is between -1 and 1. It has to be exponential decay for this to work. All right, so let's take a look at this. So notice this is infinite, okay? So we can only use this formula if this common ratio is between -1 and 1, which it is. So we're going to find this infinite sum. We need the first term, and we get that by plugging in 0. Oh, sorry, that was the wrong decimal. 0.5 to the 0, which that's just 1. So our first term is 5. And then our common ratio is 0.5. So we have 5 divided by 0.5, which is 10. All right, let's check out the next one. Let's see. We know our first term. We can only do an infinite sum. Remember, this means it's infinite. We can only do an infinite sum if the common ratio is between 1 and -1. And it looks like we're multiplying by 1/5 on all of these. Yep, that's what we're doing. Okay, so our sum is going to be our first term divided by 1 minus 1/5. So 5 divided by 4/5. Dividing fractions is the same as multiplying by the reciprocal. And so we get 25/4, which I know you could do that as a decimal. I'm going to leave it as 25/4 because I like that number. All right, we got one last problem for this section. An investor deposits $50 on the first day of each month in an account that pays 3% interest compounded monthly. What is the balance at the end of 2 years? All right. So since we are accruing interest, this is a geometric sequence, okay? It's finite because we're only doing 2 years worth, okay? So we're going back to the formula Sn equals A1 1 minus r to the n over 1 minus r. Okay, so we're depositing $50 on the first day of each month. So January 1st, $50, February 1st, $50, so on and so forth. And then the interest keeps compounding monthly. All right, so at the end of 2 years, that's going to be 24 months. So A1, that was our initial amount, that's $50. And then 1 minus our rate. Our rate is 3%, but remember it's 1.03 because it's on the whole thing. Okay. To the 24th over 1 minus 1.03. And this is financial terms. If you take personal finance, this is called an annuity. If it's a debt, this would be like a car loan or a house mortgage where you're paying a monthly payment. They also use this formula, which is pretty interesting. But this is not personal finance. So after 2 years, you have $1,721.32. Now, what I want you to think about is if you had just taken this $50 every month, you have $50 and you put it in a shoebox under your bed. Okay, if you do the shoebox method of saving money, you're going to save $50, not for 48. You're only doing it for 2 years. Okay, so if you are just shoving this money, under your mattress or whatever, you would only have $1,200 saved. So by earning interest on it every month, you've made significantly more, which is why annuities are a good form of savings. So those are geometric sequences and series. I hope you enjoyed these videos.